Okay, guys, so here's H-16. So we're going to do two examples. So we're going to do number one from the practice, but there's two parts to it. So you're given the velocity graph. So this is like the graph of the first derivative of position. So it doesn't say like the units or anything. Okay, if they're not giving you the units, then you don't have to like say them, but so this could be like miles per hour, feet per second, something like that. So, all right, at what time or times is the particle at rest explained? So guys, you're gonna need both of these, you're gonna need to have both of these in front of you. I will make copies of these for, for you guys, so I'll give them to you like while you're here, like when you're here at school. If you are at home and you have a printer, then you should print them because you really want them like in front of you. And at a certain point, I'm going to ask you to write them over and over and over because when you get the AP tests or the recall test that's coming up, the very first thing you're going to want to do is write these down so that you can refer to them. Okay, so at rest, when is a particle at rest? When its velocity is 0, all right? So this is the velocity graph. If it were the original graph, you'd be looking for something different, but this is the velocity graph, so we're looking for when this graph is 0, all right? So at what times is the particle at rest? All right, so this is part A. So it's going to be 0 when it crosses the x-axis. So right here at 3, again here at 11, and at 17. At t equals 3, 11, and 17. And then they're asking why, and we'll say because v of t equals 0. And I wrote in my notes at these times because I just thought it sounded better. So let me say that. I'll say because v of t equals 0 at these times. You could just say at because v of t equals 0, that's fine. All right, now part B. At what time or times does the particle change direction explain? Okay. Now, so we're looking, they're asking us questions about the particle. So here's the, the position of the particle itself. So the position function, and it's telling us this stuff about the particle. Okay. So changes direction is right here. So how do we know if the particle changes direction? We're going to see a sign change on velocity. So guys, if you're looking at a velocity graph, where it changes sign, so where it changes from positive to negative, or negative to positive, is when the graph crosses the x-axis, all right? So the times are going to be at 3 and 11, but guys, at 17, you can't tell. You know the particle is at rest at 17, but the graph stops here completely. So we don't know if it continued, we don't know if it would have continued to go down, crossing the x-axis, in which case we would know the particle changed direction, or it could just touch and go back up like that, in which case the particle would not have changed direction because there wouldn't have been a sign change. It just like, it was, so velocity is positive here. So the particle would have been moving to the right, took a little rest, and then kept moving right because the velocity would have stayed positive. So 3 and 17. So 3 and 11. All right, and then they say why, and I'll say because. You gotta, use this. This is why right here, because v of t changes sign. Notice, since we are given the graph of velocity, our explanations need to end with because something about velocity, all right? So, C. Over which intervals is the particle traveling right? Explain. All right, so moving right or up, okay, because we could be thinking of traveling along the y-axis. So velocity's got to be positive. All right, so this is part C. I'll move over here. So from 0 to 3, so we're looking for where it's above the x-axis, the graph. And then from 11 to 17, because v of t is positive or greater than 0. D, over which intervals is the acceleration of the particle positive? Explain. Okay. Alrighty. When is the acceleration of the particle positive? Guys, the only thing that this chart has to deal with acceleration with is in reference to whether the original or whether the particle is speeding up or slowing down. There's really no criteria here that's going to tell you about, well, the acceleration will be positive if, you know, something else happens. So this is where we need Susan's table, and we need to recognize that acceleration is the second derivative. So you're looking for where the second derivative is positive. We're looking at the velocity graph, okay? That's the first derivative. So in order for the second derivative to be positive, what does that mean about the first derivative? Increasing. So the acceleration is going to be positive if velocity is increasing. So this is the velocity function. So we're trying to figure out where this function, where this graph is increasing. And that is from 7 to 14. From 7 to 14. Now, remember, our explanation has to end. It doesn't just need to say something about velocity, but it's got to end with something about velocity. So I'll say because v of t, and I really want to be clear, you know, about this being the first derivative. You don't have to do that, I guess, but because v of t, which is, you know, the first derivative, is increasing. E, that's the last one. Okay, I'll do a second video too, guys. All right, over which interval or intervals is the speed of the particle increasing? Okay, guys, speed of the particle increasing. Speed of the particle increasing. I've never actually phrased a question to you guys like that yet. Speed of a particle increasing, that is the same as speeding up. All right. Speed of the particle decreasing would be slowing down. All right. So over which intervals is the speed of the particle increasing? All right. So that would mean, so speeding up. So speeding up, we need velocity and acceleration to both be positive or both be negative. So I'm looking at this graph. I'm looking for where acceleration is positive and velocity is positive, or acceleration is negative and velocity is negative. So, okay, let's look at where velocity is positive, all right? Velocity is positive here, okay? But acceleration is negative, all right? Because acceleration would be acceleration is the derivative of velocity. So here, the slope of the tangent line is negative, but the graph itself is positive. So here, velocity and acceleration would not have the same sign. All right, let's look at this part here. Here, velocity is positive, and also since it's increasing, acceleration is positive. All right, here, velocity and acceleration have opposite signs. So here is a place. All right, so I could say from 11 to 14 because velocity is positive and acceleration is positive. Okay, but now let me look for where they're both negative. So I've already dealt with above the x-axis. Now let me look where velocity is negative and find on that part of the graph where acceleration is also negative. All right, so velocity is negative on this whole thing. And just on this part is where velocity is decreasing. All right, so where velocity is decreasing, that's how I actually should be phrasing it. Where velocity is decreasing, acceleration is negative. All right, so yeah, so it's this part here where both velocity and acceleration are negative. So, and then also, should I do union? Yeah. All right. Okay, I'll say also from 3 to 7 because velocity is less than 0 and acceleration is also less than 0. Okay, guys, for the next one, all right, for this one, it's the same graph, but we're going to talk about how to get the speed graph from the velocity graph. That's gonna take more time, so I'm going to do this in a separate video. So there's going to be a part 1 and a part 2.